talk tonight about cataracts and the amateur astronomer. And this started with a paper that Joseph gave to me last summer called Cataracts and the Amateur Astronomer. It's by Kathy and Jerry Oltion. And I'll tell you in a few minutes who they are. But Joseph said this is probably a good one for the group, for the astronomer club, since many of us are in an age where cataracts are becoming more important. And so that's where it is. So I went over the paper, and I'm just going to present to you some of the key features of the paper and about cataracts, but I'm also going to talk about physical optics, about diffraction, because diffraction plays an important role in one of the complications that Kathy experienced. This paper comes from, first of all, before I do that, okay, there we go. Jerry Olton. He's kind of an interesting guy. From 2016 to 2025, he was a columnist for Sky and Telescope, and he worked on the amateur astronomer's workbench. Before I go on, Randy, is there a way we can get rid of the scribble that's on here?
Yes.
What was that? Oh, there we go. Perfect. Okay. Now we're back in.
There's that laser pointer thing.
Okay.
Right there. Okay.
So if I click on it, it will go to the next slide. No. Yeah, there it is. Okay. He's also done some writing. He's published 15 science fiction novels and 150 stories over the years. So he has a very creative mind. He's had multiple other jobs, from being a carpenter and an oil field worker to a DJ and even a garbage truck driver. He's had a lot of experience. And most of all, he's an amateur astronomer. Now, this is the front page of his paper. The paper comes from an experience that his wife Kathy had with cataracts. She developed cataracts and had the usual cataract extraction procedure, and then ended up with an interesting complication. And so that's what this is all about, this paper is about. And this was actually published in Sky and Telescope, I think in 2014. I think it was up there.
Yeah,
2014 issue of Sky and Telescope. And if you go to his website, to Jerry Olton's website, you can then download a copy of this paper as well if you're interested in reading it further. So what I'm going to do is first review the anatomy of the eye. Then we'll talk about cataracts, the pathology of cataracts and the treatment, how they're treated. And we want to consider what can go wrong. And as I mentioned, diffraction plays a big role in this. And then finally, the solution to the diffraction problem, to the problem that Kathy had. And this was based on Kathy's experience. I know you've all seen eyes, but you perhaps have not seen the eye with a slit lamp examination. This is a slit of light that an ophthalmologist can use to examine the eye, particularly the tissues that you normally don't see because they're clear. This is a beam of light. It's about 1/10 of a millimeter wide and as high as the top of the eye. And as you can see, it lights up, first of all, the cornea, which is right here in the front. This is the part of the eye that you put your contact lens on if you wear a contact lens. It's about 1/2 millimeter thick. Behind that is a clear chamber called the anterior chamber, and that's filled with a clear fluid called aqueous humor. Now, here is the iris. That's the part that gives you the color of your eye, and this is the pupil, an opening to the back of the eye where light has to go. Now, look in the pupil here where the slit goes. You see this here? This is the crystalline lens, and this is what can deteriorate and become a cataract. You see a little bit of scatter from that. Now, if you look at the eye in cross-section, here's what we just looked at. This is the cornea, anterior chamber, and here's the crystalline lens. These structures perform the role of an optical system. So they gather light from the outside world and act as a lens to project an image of that light onto the retina, which is in the back of the eye. And the retina serves a sensory function. It senses that light, sends information about the pattern of light to your brain, where your brain interprets it as the scene that you're looking at. Okay. Yes.
Question for you. So the aqueous humor was between the cornea and the lens?
Yes.
And that's different from the vitreous behind the eye?
That's correct.
Okay.
The area behind the crystalline lens that fills this area here is called the vitreous humor. And unlike the aqueous humor, as I mentioned, is like water. It's very thin, and it'll drip. Vitreous humor is thick. So in a young person, the vitreous humor, if you put it out on a table, it would look like Jello. As you get older, it becomes more liquid. It liquefies. Okay. So you have the aqueous humor and the vitreous humor. Now let's look at the anterior segment. Again, to review it. There's the cornea. The anterior chamber is there. Pupil is right here. The lens capsule is here. And this little thin blue line is a capsule that goes all the way around the lens. And the crystalline lens is inside of that capsule. The crystalline lens allows the optical system to change its focal length, and that's the role it plays. It has about a third of the optical power of the entire system, a third to half of the optical power. Most of the optical power is actually with the cornea, and it's because of the big change in refractive index between the air and the corneal tissue. Now, the lens is immersed in fluid, and so there's not as big a change in the refractive index, so it doesn't have as much power, even though it looks like it should be a pretty powerful lens. So this is what the crystal lens looks like. You start out when you're born with just nucleus, or before you're born, a nucleus, and these layers are added to it as you grow up. And these are made out of proteins that are in lamellae, or layers, sort of like the layers in an onion. Now, the advantage of that is that if you stretch the crystalline lens, it becomes flatter. If you relax it and bring the outside in, it becomes thicker. And that changes the optical power of it. So this is a way of allowing us to change the optical power of the optical system so we can focus on things in the distance, and we can focus on things up close. The other thing is the lens is made up of proteins. Now, why is it clear? Proteins, if you look at proteins in a bottle, they're cloudy or they're hazy. The reason it's clear is because these proteins are arranged molecularly in a very uniform spacing. And light, as it goes through it, encounters them, and you get constructive interference going forward. It's just like a crystal of quartz. You can pass light through it, and there's silicon atoms in the quartz, but they're spaced out in such a way that the light is able to be transmitted. And the same thing happens with the crystalline lens. Okay. One other thing, if you look on the sides here, there's these structures. These are suspensory ligaments, and these are attached to the lens. These are attached to a muscle that can pull on it or relax. Okay, now let's look at accommodation. The ability of the lens to change its focal length is called accommodation, because you're accommodating to near or far. So if you have an object like a star that's off in infinity, that's here, and I just have an arrow showing that it's way off to the left. The light from that, when your lens is relaxed, or it's actually under tension, when it's flat, this optical system brings us to a focus on your retina. Now consider what happens when an object comes closer to your eye. Well, as you all know, with a lens system, you bring an object closer to the lens, the image goes farther away. And so that image doesn't focus on the retina. You get a blur image. So what happens? The ciliary muscle, which is up on the side, it's a circumferential muscle that goes around the outside of the lens and attaches to these suspensory ligaments that I just showed you. That muscle contracts, and it's attached to what's called a zonule, and this is the composition of these suspensory ligaments. When that contracts, it becomes tighter or smaller. Remember, it's around the outside, so if that muscle contracts, it comes in. That relaxes these ligaments, and what happens to the lens? It gets thicker. So the lens becomes shorter, and it gets thicker. That changes the optical power of it, and now that focuses the image. So that's called accommodation. And that's really the function of the crystalline lens in this optical system, is to allow us to focus on things in the distance and focus on things up close. So that will change and maintain it, and that maintains a clear image, regardless of whether an object is off in the distance or up close. Now, as we get older, the lens becomes stiffer, and so we lose the ability to accommodate. Then we have to wear bifocal or progressive lenses. We have to have a different optical system, a different lens or glasses to be able to see things closer. Okay. So here's when it's out of focus, and here's when it's in focus. Now there is a comfortable reading distance. We typically, and that's about 25 centimeters. So when we're reading, we're accommodating, and that's what we're comfortable with, at least when we're younger. When we're older, we lose that elasticity. We have to put in an auxiliary lens on them. Okay. Now, cataract, pathology and treatment. What is a cataract? A cataract, okay, here we go. Now, what I just showed you was was what we're seeing here. If you have a star out in the distance and you're not accommodated, your lens is set up for distance vision, you get a clear image on the retina. Now, imagine what happens if for some reason you get some material in the lens that doesn't belong there. Or if these proteins that are in the lens start changing their characteristics and they become opaque or become translucent. What happens to the light as it's going through there, it'll encounter these things and scatter. And that means that the light, instead of going in a straight line, is pushed off to the side slightly. And so what you see, this is the normal, and the scattering will bring the light off to the side, as you see here. So instead of seeing a nice clear image of a star, you see a star with a halo around it, or it falls off. And the same thing is when you're out in the street at night, you see street lights, you're going to get these halos around them, and you're going to get distortion from that. So this is what's called forward scatter, and we experience this as what we call glare. So people refer to glare, they're talking about light being scattered and being spread across your retina when it should be in one point. Now, another thing that can happen is you can have local defects in the lens. And if you have local defects in the lens, as you're seeing here, these areas will focus in a different place. So they will not only scatter, but they will spread the light so that you see multiple images. So instead of having one image of the star, you're going to get multiple images. So both of these things can happen in a lens, depending on the particular pathology that you have and the characteristics of the way the cataract develops. You see multiple images under these circumstances. Now, let's go back to Kathy. This is what she was experiencing. When she looked at Saturn through a telescope, instead of seeing one image of Saturn, she saw 3 of them. And that suggests that her lens had these local defects in it. And so that was spreading it out, and she was seeing multiple images. Now, how do you fix that? Well, the easiest way to treat a cataract is to remove it. So you remove it, but then you have this optical power that you have to replace. If you remove the lens, the crystalline lens, and just leave it, you've lost about 1/3 of the power of your eye. So it's very difficult to get that back. You'd have to have very thick glasses. And back in the days before they put in replacement lenses, that's what happened. They took the cataract out and you could see light, but you had to wear a very thick set of glasses to make up for that optical power that's lost. So now what we do is we replace the defective cataract, the defective crystalline lens, with an artificial lens. And this is called an IOL, or intraocular lens is the usual name. This technology was first done in St. Thomas's Hospital in London by a doctor named Sir Harold Ridley. And he did the first successful intraocular lens implant in November of 1949. Now, he had a very interesting way that he came up with this idea. He was a physician. He was an ophthalmologist for a fighter pilot in World War II. And this pilot was flying a Spitfire. The Spitfire has a plexiglass canopy, which is bulletproof. So when bullets hit it, they would bounce off. But some of the bullets would hit it with such an impact, the plexiglass didn't shatter, but it sent little shards in. So the bullet would hit it, and you get a divot in there, bullseye, and it would send little shards in. And this particular pilot got some of these in his eye. They were embedded in his eye. And Dr. Ridley followed him, and when he looked at that, he said, I think I want to take that thing out. It'd be too complicated surgery. I'll just leave it in and see how it goes. It was outside of his line of vision, so it wasn't a real problem. So he did, and he followed this patient for several years, and the eye did not react. Now, normally, if you put a foreign substance in your body tissue, you get a reaction, but this did not. So he realized that plexiglass, which is also called polymethyl methacrylate, or PMMA, is inert when you put it in the eye. So he started thinking, maybe I could make a lens out of this and replace the lens, the cataract with it. And so he did. Now this material, PMMA, you can mold. So you can mold it into a shape, you catalyze it, and it hardens. You make a rigid lens, and you put that in the eye. So he did this in 1949, was the first one, and it was successful. Now the ophthalmology community was not overly enthusiastic about that because they didn't like putting things into the eye. But when they found out how successful it was, they started doing it, and ever since then we've been replacing cataracts with intraocular lenses. The technology has changed quite a bit since 1949, and I'll show you some of these changes as we go along. So, Kathy's cataract procedure. Let me show you how this procedure is actually done in today's world. First of all, there's two things. You remove the cataract, you insert the intraocular lens. How do you go about this? Well, the first thing you have to do is open up the capsule. Remember I mentioned the capsule that goes around the crystal lens. That's a barrier. You got to open that up, and you can do that through a small incision. You make about a 3 millimeter incision in the cornea. You can put some very fine instruments in there, and you can scrape around the edge of the opening that you want to make. You generally make a round opening. You want this to be about the size of the pupil when the pupil is fully dilated. You want to maintain some integrity there, but you want to have it large enough so it's not going to interfere with your sight when the pupil is widely dilated. So that's what's being done here. And you can see how this is round, and you remove that little piece of tissue. Then you've got this cataract under here. How do you get that out? Well, there's a device called a phacoemulsifier. And this is a little probe that you can insert into that 3 millimeter incision. It goes to the cataract, and it has a little, I guess you describe it as a pin, a little plunger on the end of it. And that plunger can move back and forth, and it goes through a stroke of about 50 to 150 microns. Now, that's not very much, but it does it at a very high rate. It does it at 35 to 45 kilohertz. So this is ultrasonic. And what it does, it creates cavitation. When you make things move that fast, you create cavitation, it pulls a vacuum, things implode, and it will break up the cataract. And so you can chop up this cataract. At the same time, there's a port that flushes saline in and aspirates saline out. So you break up the cataract into little tiny pieces, you flush it through, and then pull it out through the aspiration. And within about 10 minutes, you can completely remove the cataract and polish up the capsule and clean that area very well. Okay? So that removes the cataract. And this is much easier than it used to be done. Back in probably 30 or 40 years ago, they used to remove these cataracts in one piece. And then it took a much larger incision. You couldn't do it through a 3 millimeters. You almost had to make an incision across half the eye. So this is much easier, much less invasive. It takes about 10 minutes, and you can get this cataract removed. Then the next step is to insert the crystalline lens. Now, this is another ingenious thing. You can see that lens in there is, the diameter is about the size of the pupil. It's fairly big, maybe 5 millimeters, 6 millimeters in diameter. How do you get that through a 3 millimeter incision? The intraocular lenses we have now are flexible. So we can make them out of material that can be folded, and you can actually roll this lens like a taco, put it into an inserter that goes through that 3mm incision. When you put it inside the capsule, you pull the inserter out, the lens unfolds, and it's there. Now, if you look carefully at this, you can see that you have the lens, which is this part right in here. You also have these two little things that look like wires coming off. And on a real lens, they look like fish line. These are called haptics. And their role is to stabilize the lens. So these haptics go into the corner of the capsule, of what's left of the capsule. You can see that here and here. And they fix themselves there, and that keeps the lens in position so it doesn't drift around, doesn't shift around. These haptics actually will play a role in the complication that we'll be looking at here. So just keep that in mind, what they're doing. And so that stabilizes the lens. Here's a picture of a slightly different design of an intraocular lens, but you can see what this looks like. It's nice and clear. These are the haptics coming off here. Now this particular one, the haptics are molded right into the lens, and this will work just as well as the other one. I think the other design was more common. I'm not sure how often these are used versus the other type, but so there's some different designs, and some of these have some different specific purposes as well. So Kathy had this done. She looked at Saturn, and this is what it looked like. She no longer saw the three images. She saw one image, which is good. But what are these lines, these spikes going on there? These things were coming out, and this was bothering her. So what does that remind you of? It reminds you of diffraction spikes when you look at a bright star through a Newtonian telescope, sort of like this. This is a picture I got from Adam Block of NGC 2419, which is C25. It's this globular cluster right here. But look at these bright stars that are next to it. This is why I chose this one. You can see these bright spikes coming up, and these are diffraction spikes. Question is, could this be what's causing the spikes on Saturn? And if so, what's causing the diffraction? Okay. So let's go on. What could go wrong? Could it be diffraction? And now, to understand whether diffraction plays a role or not, we need to understand something about diffraction itself. And here's where I want to go get off on a tangent. We'll get away from this, and we'll come back to Kathy's story here. There's a couple of things that can change the path of light. One of them is reflection. You have a smooth surface, light will shine on it and it'll be reflected. We're all familiar with reflection from a mirror, from surfaces of glass. Anytime you have an abrupt change in the index of refraction, you can get reflection. Refraction is the other thing. Light comes in, you have a change in the index of refraction, light will bend. And you're all familiar with that, looking at water and seeing the image in a different place than that you expect it to be. Scatter is the other thing, and this is something that we just talked about, scatter from materials that interfere with light. And finally, diffraction. And diffraction is something that happens when light is attenuated by a stop of some kind. And let's just look at that. To understand diffraction, you need to review what light actually is. Light is an electromagnetic wave. And this means that the electric field oscillates up and down at a very high frequency as it's propagated forward, and it has length from peak to peak. Okay. Now for light, for visible light, the wavelength goes from 400 to about 700 nanometers. And a nanometer is 10 to the minus 9 meters. Okay. The violet is in the shorter wavelengths and red is in the larger ones. The frequency of light is 400 to 700 terahertz. Now, terahertz is 1,000 gigahertz. So we're all familiar with gigahertz from computers. So this is quite a bit faster than computers are oscillating. It's faster than anything that we have other than that generate light. The wave characteristic is what's described here. Light also has particle characteristics, and these are called photons. If you start to reduce the intensity of light, you would expect that if it was just a wave, that wave would get smaller and smaller and smaller and finally vanish. What actually happens, if you make the proper measurements it doesn't just get smaller and smaller and vanish. What will happen is when you get down to these very low intensities, the light comes in pulses. And these are photons. So a photon is a packet of light. It's the minimal amount of light that you can have. Now, the particle characteristic we're not going to deal with tonight because the diffraction comes from the wave characteristics. So let's look at some of these wave characteristics. Interference. Suppose you have two rays of light coming together and they are in phase. In other words, the peak is lined up with the peak of one is lined up with the peak of the other. Well, if these are going to the same place, these can add together and you get a very strong light and you get a bright area. Now, suppose we could put in a delay on one of the paths, and not much of a delay, just enough to slow this second beam down by half a wavelength. Okay, what that means is that the peak is going to correspond to the trough. These rays will also add together, but the result will be essentially a flat line here, and you get a dark spot. The top one is called constructive interference, and the bottom one is called destructive interference. You have constructive interference give you a bright area, and destructive interference gives you a dim area, or loss of light. Now, let's look at wave propagation through an small opening. These vertical lines represent the peak of the peak of a wave. The other thing that you can do is that we can assume is that the wave is made up of multiple point sources that go along one of these wavelines. And in fact, there's infinitely many of these. They're very close together. And if each of these is a point source, remember a point source radiates 360 degrees. The light goes in all directions from a point source. If you have a whole line of these things, and there's infinitely many, it's going to look, the waves are going to look something like this. So this one on top here has a 360 degree radiance going this way. The next one is the same way, and all that down. You get many of these together, and if you look at this carefully, what you see is at the next top of the wave, these are all coming together. And so you're getting constructive interference at this point. In between, these wavefronts are not coming together, so they're going to be out of phase. So you're going to get destructive interference. The net result of that is that you have a plane wave that's moving forward, even though it's made up of all these little point sources. So you can describe that as a wave that looks like this. Okay? Now, what happens when that wave comes to a small opening? Suppose it goes up to there. Well, all of these are blocked. You just have one that gets through, or a very small number of them. Now, one is an exaggeration, but you have a small number of them. So that particular point source then behaves as a point source on the other side of that opening. And so this means that this is the wavefront. The wavefront is now curved. And at this point, you've got a ray that's going this way. You have some that are going this way and some that are going down. The peaks of all these line up on these lines. Okay. This happens with light. It also happens with water waves. If you have, for an example, and I don't have a picture of this, but if you have a pier and there's an opening in the pier for boats to go out, and you have big waves coming in, rolling in, you look at the waves on the other side of that opening, they will actually be circular and coming out. So it's the same thing that you're seeing here, the same kind of behavior. It's a wave phenomenon. Now, how does this lead to diffraction, and what is diffraction? Suppose the easiest way to explain it, suppose we have two slits, like you see here, spaced one next to the other. You have one here, the wavefront is coming in, they're lining up, and when they get to the slit, you now have two point source transmitters. Well, let's look at the path from these going forward. The distance from these two points to here is the same, so the waves are going to be in phase. And that means you're going to get constructive interference. You're going to see a light spot. Now let's go off at a slight angle. And this angle is such that the difference in the distance on this lower wave is half a wavelength longer than the upper wave. That means that these waves are going to be out of phase. So the peak here is going to correspond to the trough. That gives you destructive interference. And so you will not see a bright spot. You will actually see a dark spot. Oops, I don't know what, okay, there we go. You will see a dark spot. Now let's go a little further. Let's go up here. In this case, the distance of that lower one is one complete wavelength more than it is for the upper one. That means that these waves have come back in phase, and so you're going to get constructive interference here. You're going to have these alternating light, dark bands from those two apertures. Okay, and this is what we call diffraction. The diffraction is this light going sideways, apparently sideways, or with these alternating bands. Now you can have the same thing with, instead of having two blocks, suppose you just had one obstruction, as you see here. You get the same thing. These two become dominant because you're missing the ones here, and so you can get the wave paths that are going forward are going to give you constructive interference. Come on. You're going to get one that's half a wavelength difference. It'll give you destructive, and one complete wavelength difference, and that'll give you these bands that you're seeing here. Now notice you also have, I didn't draw the arrows, but you also have it going the other direction. So you get the same effect on both sides of the obstruction. Okay. And this is similar to the two-slit, but it's a little bit weaker because you have these other lines here that are also transmitting. So you have plane waves out here, and that's superimposed on this diffraction. But it is bright enough to see. So if you have a Newtonian telescope where you have a support for the secondary mirror, as you see here, if you have just one support, you're going to get diffraction going sideways like this. Diffraction is always perpendicular to the obstruction. If you have two of these supporting it, you're going to get a brighter diffraction. If you have two of them that are 90 degrees, the diffraction spikes are going to be 90 degrees. And if there's only two of them, they'll be weak. If you have two in one direction and one in the other, you have a bright one going perpendicular to the two and a weaker one there. And finally, with four of them, you're going to get four brights. Now, if you have three of these, like here, as you see here, you're going to get three sets of diffraction spikes because the diffraction spikes are always perpendicular to the obstruction. Okay. Now, you can actually create diffraction with this device. This is called a Bahtinov mask. And what is this good for? Well, it creates diffraction in a telescope, but each of these areas is a different part of the lens. So let me show you what this looks like, and we'll tell you what good it is in a few minutes. You put this over in the front of your telescope. I put this in the front of my my Sea Star, and I took a picture of 19 Auriga with a diffraction, and you can see there that it creates three diffraction lines that are on there. Now, since these are coming from different parts of the lens, when the microscope is out of focus, they will not intersect, at least in one point. But when it's in focus, they're going to come together, and you're going to intersect in one point, and that's sometimes easier to see than trying to judge focus based on the blur. So this is a tool that you can use to create a good focus on your telescope, particularly when you're using a camera for it. Now let's look at this up close, a little closer here. You see that there's a couple of orders here. This is the primary star right here. This is the first order. So this is the first place where these lines are getting out of, or one is getting out back into phase after being out of phase. Then there's a dark band here, and then you see this here, and you see this rainbow. The reason you see the rainbow is because the angle that gets diffracted is wavelength dependent. Remember, it depends on whether it's a complete wave difference or not, and that wavelength for blue is shorter than the wavelength for red, so blue is going to appear sooner or closer to the center than the red. And here you're seeing different orders. You see this is the zero, we'll call this the zero order. This is the first order, this is the second order. There's another one out here, third order, even fourth order. These get weaker as you go farther out. because of the there's just not as much going out that way. Now notice you only see this on the bright stars. You don't see this on some of these faint stars. They're there, but we're not picking it up because they're quite faint. And also the brightness out here is faint compared to the zero order. Now one other thing here, if you just look at this carefully, you see these little spikes out to the side. Where is that from? Well, if you look back at this Batinoff mask, this vertical line actually creates a diffraction going sideways on there as well. Okay, let me get rid of this thing here.
Lines just went straight. I mean, if there was no line separating them.
Oh, lines. Well, it'd be difficult to make a mask like that. It would. You have that top, that ridge. You're talking about this thing here.
Yeah, that ridge, that really perpendicular.
Oh, I see. Yeah, yeah. It probably would. You'd probably get rid of that on there. It would be less. There'd be less strength in it. I think there's some practical things that you'd have to deal with, but theoretically you wouldn't see that on there. There should also be one going vertically as well because of that. Although there is a little bit of a horizontal thing there. It's not very strong. Randy, can we get stop share? Oh, you want that on there?
Yeah.
Okay, that needs to be on there. Yeah. Okay. Yeah. Okay. Now there's one other effect, or one other place where you see diffraction in a telescope. And anytime, as I said, anytime you have a stop, something that blocks light from the telescope, you get diffraction. With a refracting telescope, you don't have these secondary mirror holders, but you have an aperture. And that aperture causes diffraction as well. And this was described by George Biddle Airy, and 1801 to 1892, and he was a British astronomer and mathematician. He described what was going on here. So consider if you had a lens that's completely corrected, all the aberrations are going to this perfectly corrected lens, and you have an object out here that has a square function, so it's bright, and then it's all the way across, it's like a disk, or even a star, for example, it's very small. And you make an image of that. That image doesn't look exactly the same, but it looks like this. Now this is exaggerated. This is blown up. But you don't see that sharp image. You see a spread of that image, a spread function. And you see these dark bands around it. And this is called the Airy disk. And Airy went through the mathematics of this, and he found that this is what it looks like. And you can even describe the width of this, the full width at half maximum. That is, if you take the maximum, go to half, and measure the width of this bright area, it's approximately equal to 1.029. I don't know why I say this approximately. 1.029 times the wavelength of the light divided by the diameter of the aperture. Okay. So this is why, if you have a small diameter telescope, that Airy disk becomes larger. And that means that your ability to resolve two stars that are very close together goes down. It's much more difficult with a small aperture. If you increase the diameter, then that full width at half maximum gets smaller. And so you can now separate two stars that are close together. And this is all because of diffraction at the edges of that lens, at the top and bottom of the lens. The diffraction plays a role in just about any optical system that you have. And this really limits the ability to resolve small objects off in the distance with it. So when you see these dime store or these department store telescopes, 60 millimeters, they say you can use 400x. Well, you can use 400x, but your objects, the Airy disk on that is going to be quite large because it's a small diameter of aperture.
Is there a relation to this and this on the Gauss limit then?
And the
mathematical relationship between the Airy disk and the Gauss limit?
Yes, it is. Yeah, the Dawes limit is I think it's the separation. I think that you can do it, and you can come up with using a similar equation. You can come up with the distance between two just resolvable objects like stars with the aperture that you have. Yeah, yeah, and that's based on the same mathematics as this. And he figured this out based on diffraction theory. Okay. Now, I want to demonstrate a couple of these things on diffraction. We just talked about diffraction. I can actually show you what diffraction looks like in a practical sense. I've got my laser pointer here, and I've created some diffraction objects. I've got a couple of them. One is two razor blades that are close together. They're about 0.2 of a millimeter apart. Now, as I showed you on here, we should get a diffraction from that. The other one is a single piece of fish line, and it's braided line, so it's not clear. So we'll see if we get diffraction from that. And the other has 3 pieces of fish line that are close together, and we'll see what that. So let's just try the first one here. This is the blade. If I can get this just lined up right, I think you can see it pretty well there. Do you see it? All see them? So you see the primary one is the one in the middle. It's the brightest one. But look off to the sides, and you see these dotted lines going out there. These are the diffraction, the different orders of diffraction. And because this is so wide compared to the wavelength of light, they're very close together. If you have a wide diffraction gap, which is large compared to the wavelength of light, these bright areas get closer together. That's what you're seeing. Yeah. This is the razor blades, the 2 blades. So it's basically a slit. It's a slit aperture on here. And that's creating, you can do it with blades very easy because you get a nice smooth surface. I can tape them onto this piece of wood and get that through. Okay, now let me try the one with just 3 pieces of string. So now you don't have a gap, but you have 3 pieces of string and the rest of this is open. And very similar. Not quite as clean because the thread is not as clean as the other one, but you can see the see that? Okay. Now how about 1 piece of string? You think 1 will do it? Remember we saw that 1 obstruction would create some diffraction. And sure enough, it's not as bright, but you can see it going horizontally. If I turn it like this, you can see it going vertically. Now you don't see the individual bright and dark bands on it because it's kind of spread out more with just 1 thin line on there. But you do get diffraction from a single thread going down there. It's not very bright compared to the brightness of the laser, but it is there. And we'll look at that in just a few minutes. Now, here's another thing. Randy handed out these diffraction gratings. This has 500 lines per millimeter. Now, what do you suppose will happen when I shine my laser through this? Now, remember, the laser is 1 wavelength. And so it's spreading out. If these are close together, the distance for that first order is going to be farther away. And in fact, it's quite a ways away. You can see the first order, the second order, and there's probably a third order there, but it may be too far out to see it.
Wouldn't blue laser have lines that are closer together?
They would, and red would be farther apart. I didn't bring any of those other ones, but I did bring a flashlight. And let's see what we can do with this. Now this is spread out. I couldn't get a nice small spot with this because it's incandescent. But here's what the thing looks like. And if you look at that, now it's a little, there you can see it. It's a little faint on here because the light isn't all that bright. But you can see the rainbows on the side. You see the violet being close to the original image, the 0 order. Then it goes into yellow, green, yellow, and then finally red on the side. So that is an image of the spot that we've got here of this thing being diffracted. The whole thing is an image. Now, if we wanted to do a spectrum and actually look at the spectrum of light like on a star or something so we can determine what materials are in that star, you'd use the same type of thing. You'd use the same type of gradient. But what you would do is you'd put the light through a very thin slit. And then when you shine that on here, you get an image of that slit. And that's what's referred to as a line. So we talk about different lines at different wavelengths. That's the image of that slit going through a diffraction grating that goes through there, and that position of those lines corresponds to a different energy in the molecules or the atoms that are being excited and then emitting light. And that's how we can determine what materials are in a star.
It's perpendicular to that grating.
The slit is parallel to the grating.
Parallel.
Yeah, so it's being diffracted sideways. If you had it perpendicular, it would diffract sideways, but the whole slit you get the image of the whole slit smeared out.
Okay.
So you want to do it the same.
Parallel.
Yeah, parallel slit. Yeah. Now, one other thing I can show you, my laser came with a little attachment. Let's see if you can figure out what this is. What's going on there? Well, it's pretty easy. There's a diffraction grating in here going in two directions. And so you're not only diffracting sideways, you're also diffracting up and down. And you get that nice thing. So you can, when you buy these lasers, for some reason, they always sell one of these. They always include one of these little diffraction things. And you can get some different patterns, and that's based on the
Is there a spin to change the spacing?
no, it doesn't change the spacing, but it changes the orientation. So if I spin it,
Okay.
changes the orientation.
One that changes the spacing.
You have one that changes the spacing? Okay, yeah. Yeah, if you change the spacing, then the distance that the dots are.
Is it two? Is it just moving one versus the other? That would move the distance between the two?
No, because if you had two of them, now if we could do that with this. Okay, I can do the same thing with, I've got two of these diffraction gradients, and you put this through here, you're going to see a pattern like that. Now the spacing on these is much smaller, and so they're spread out more than that little one that came with it. But if I change the orientation of this, for example, do it here, it just basically changes the orientation, the relative.
So
They'll move.
Spacing dots change.
What's that?
How do you get the spacing between dots change?
Oh, they don't. The space between the dots are fixed. Oh, between the.
I'm saying when you spin one migrating,
yeah,
it changes the spread of the dots.
It's not really changing; it's changing the orientation. So it's changing one set of lines relative to the other. So diffraction, remember, is always perpendicular to the lines in your diffraction grade. So as you change it, you're changing the orientation of one.
So you're changing the orientation of one versus the other.
Yeah.
That makes sense. Okay, that's what I kind of thought.
Yeah.
Could you imagine being able to explain everything that you're seeing when it's going in all the different directions? We're looking at, you all got to look at this.
Yeah. Okay, now let's continue on. Now, what does this have to do with Kathy's cataract? Well, remember what you saw here, and I'm suspect that this is a diffraction issue. But where is the diffraction coming from? Well, to find out, you have to examine her eye. And this is what's called a retroillumination. You take a bright light slit lamp and shine it on the side of the pupil. The light goes back to the retina. You get the red reflex from the retina, just like when you take a picture and you see that red light on the person's eye. You can do the same thing with this. You illuminate the back, but you're not focusing on that. You're focusing on the front of the eye. And so what you see is the front of the eye illuminated from the back. And now you can pick out some of these structures. So for example, here is the edge of the intraocular lens. Now her pupil is widely dilated. This is more than you normally would dilate naturally. This is done with eye drops. So here's the edge of the lens. Here's the haptic. The haptic goes up here, and there's another haptic that goes down here. Remember, these are fixed in the capsule, in the edge of the capsule. And this is the capsular rhexis right here. That is the area where the capsule was open so that they could put the intraocular lens in after removing the cataract.
Did they have aqueous humor back, or is it removed? Or?
No, the aqueous humor isn't removed. It's some of it will leak out, but not a lot of it, and it reforms. It reforms as enough to you can fill the entire aqueous anterior chamber in about an hour with aqueous humor. So it's a very active pump. So that comes, and that also maintains the pressure in the eye. Okay. By the way, that wound is self-healing. You make a 3mm incision. If you do it right, you don't have to put sutures in it. It'll just close up and seal up very, very easily. Now, you see anything in here that may be suspicious of diffraction? Well, in fact, there's a wrinkle This is in the posterior capsule. Remember, you have an anterior capsule that they had to remove to put the cataract in. There's also a part of the capsule in the back that they generally leave in there. Now, where's this wrinkle coming from? Well, you have these haptics up on top. They're pushing the inside of the capsule of the capsule. So that means that they're putting tension on it. That means the sideway is going to come in. And where does that extra tissue go? It creates a fold. So that fold or that wrinkle is what's likely causing the diffraction spikes that she's seeing. Now, she brought this up to her optometrist. Optometrist's response would say, what? None of my other patients with capsular folds complain of these spikes. And apparently, a capsular fold is a relatively common complication of cataracts, but most people aren't bothered by them. And it's because if you're out in daylight, or like we're in here now, you probably would not notice them because the diffraction is relatively weak. As you saw from this laser, the laser is still very bright, but the side spikes are relatively weak. So if we're out in the street looking around, you would likely not notice these, and people are so grateful to have their vision back after the cataract is removed that they'll just tolerate it and won't bother. The time that they might see them is at night when they're looking at lights. You're looking at a bright light on the dark background, you're going to see these spikes. And people will either ignore it or when they're driving, they're bothered by it by driving, they stop driving, or even worse, they keep driving and just tolerate it. So it's fairly common, but most patients are not bothered by it. However, Kathy is an astronomer, and so she's looking at bright objects that are small. These things are going to be bothersome. So they talked with their optometrist about this. They talked about another ophthalmologist about it, and he said there's no way that could do it. Well, they were kind of at their wits' end, and they kept at it. They finally they referred to another ophthalmologist. Kathy actually had another eye her other eye had a cataract. And they described the symptom. He says, well, I'll put a ring in there. That'll keep this thing straight. And so he did the other eye, and they put this ring in. Well, same thing happened. So it didn't really help it. They finally found an ophthalmologist, a young ophthalmologist, who listened to them and realized that they kind of knew what they were talking about. And he looked into it, and he says, yeah, I'll bet that capsular fold could be a problem under your circumstances. So what's the solution to that? Well, let's talk about the solution. The solution is to remove that posterior capsule. Now, you don't have to go in like you did for the cataract. You don't have to make an opening into the eye. You can do this with a laser. And you use a neodymium YAG laser. And the laser will cut the posterior capsule. It'll go right through the lens because it's focused to a point. It doesn't affect the tissue in front of it or behind it. And you can actually cut away that posterior capsule as you see here. Now let's talk, since we're all equipment nerds, let's talk about the neodymium YAG laser. That's kind of an interesting device. Wavelength is 1064. Does that sound familiar to any of you? The 1064, does that mean anything?
Infrared.
What's it?
Infrared.
It's infrared?
It's double of 500.
Exactly. It's exactly twice the green laser that we have. This laser is 532 nanometers in the bright green. This is exactly twice that. The laser that we use for pointers, I'm not sure if all of them are, but some of them are neodymium YAG lasers with a crystal that doubles the frequency. And so that gives you double the frequency, you get half the wavelength. Okay. So that's kind of an interesting thing. This is a handheld thing. It's a device that's fairly small. And yet if you use the original neodymium YAG laser, you get this 1064. Neodymium is an element that actually does the lasing. The YAG is yttrium, aluminum, garnet. It's the crystal substrate, and then the neodymium is the material that's embedded in that actually does the lasing. So that's just for. This device uses a 3 to 4 nanosecond pulse with a pulse width of with a pulse width. 1 nanosecond is 10 to the minus 9 seconds. So that's fairly fast. Now, how fast do you think that is? Well, in 3 nanoseconds, light travels 90 centimeters. So light that travels 186,000 miles per second will travel about 90 centimeters, a little less than a meter, in 3 nanoseconds. So that is quite fast. Now, what does that do for us? Well, if this thing delivers 0.5 to 1.5 millijoules. Now, a millijoule is a watt second. You're used to thinking of energy in terms of kilowatt hours. Well, this is a watt second, and that the formal term of that is a joule. So a millijoule is 0.5 to 1.5 thousandths of a joule. Now, during that pulse time, that means that the pulse energy is about 300 kilowatts. So if you do the math, so that's a lot of energy in a very short time, but it's enough to vaporize tissue. So this will actually vaporize and cut the tissue at that focal point. I said that it's being focused down, so you don't see that action in front of or behind, but in that little tiny focal point, it'll zap it. And you can actually hear these things snap if you do it in certain conditions. So it basically creates a plasma and vaporizes the tissue, and you can cut that posterior capsule. You can do it just sitting in a chair, aim the laser at it, and there's no pain associated with it, there's no nerve endings there, and you can treat that. And what happens then? You can remove that posterior capsule. The high power density of the focus vaporizes the tissue. So Kathy had that done, and finally she got a clear eye. I don't have a retro room, but here you can see the capsule. I'm not sure if this is the anterior or posterior capsule rexus, but in any case, he no longer has that. Now this, in addition to the folds, that posterior capsule can become slightly opaque, and that's called a secondary cataract, and the treatment is the same. You hit it with the laser and cut it out of there that way. So this is a fairly good treatment, secondary treatment. Yeah.
Do you ever get secondary and not primary cataracts?
That's a good question. I don't think so. I think that it shows up either with it or after the cataract is removed. And finally, this is her appearance of Saturn when she looked at it. So she no longer has those diffraction spikes because she's removed the material that causes diffraction. Okay, now what do we take away from this exercise, from this paper? First of all, extraction and IOL placement is a great solution for cataracts. You get a cataract, it's a great treatment. You could not see very well before. You put the intraocular lens in, you can see, and you can adjust the power of the lens to give you clear distance vision, and you correct what visual defects you had before. So, I have a friend, a roommate in college. I saw him. It's probably about 10 years ago now, but he had cataract surgery fairly young. And he says, I don't know why I didn't have this done earlier. I can see so much better with these lenses in there. I don't have to wear glasses anymore. He thought it was great.
Can cataract surgery fix astigmatism?
You can, yeah. You can implant a intraocular lens that corrects astigmatism. It's a little bit more complicated because you have to get the orientation right.
Yeah.
But you can do that, and there are some techniques for doing that. There are some astigmatic lenses or cylindrical lenses that are placed in there now. Yeah.
Of course, that's more expensive.
It's more expensive. Yeah. And there's some interest.
Sure.
Yeah. There's some interesting equipment that's used for some of these. You remember we were talking about the picosecond laser, the femtosecond laser, which is even shorter than that, and that you can actually use to make custom cuts. You can make your incision. You can reshape some of the cornea to correct astigmatism. You can cut up the cataract and then aspirate it out. So there's some different technologies that are used for that. We won't get into that.
How long do these lenses last?
These lenses will last, I think, for ever, for as long as they're in your eye. They don't. Now, I've not heard of cases where they pick up material and become clouded or anything like that. occasionally you have to exchange them. But I don't think it's the fault of the lens. I think it's the way the body is reacting to it and doing things. And that's more complicated. You have to do things a little different. Second point, diffraction from a posterior capsule fold may show up at night. Bright objects on a dark background. As we look at stars, as we look at astronomical objects, this diffraction from a fold can become more apparent and can become more bothersome. This may be particularly bothersome for astronomers, bright objects on a dark background. If you encounter this, it's a good idea to discuss with your ophthalmologist the optical needs of astronomers. So initially when Kathy and Jerry went to her ophthalmologist, he didn't think that this was an issue, or optometry didn't think it was an issue. But because of their persistence, they convinced the ophthalmologist that finally did the final surgery, the capsulorhexis, convinced him that that was in fact a problem. And by treating it, they solved that problem. Your case may be unique, and so you need to discuss the options with an ophthalmologist. And don't use their paper as guidance, sole guidance, when you're considering different procedures. You got to talk to your ophthalmologist about what the options are, but make them aware that some of these things can affect your vision, and particularly at night. Your case may be unique if you need to discuss the options. Further treatment is fairly simple if it's needed when you see diffraction spikes. Now, one thing I'll quote from their paper, if you go into cataract surgery informed, you stand a much better chance of coming out of it happy. And this is what their conclusion was in the paper. One last quote from the paper, I see that guy. So I want to give special thanks to Jerry Olchin, the contributing editor for Sky and Telescope, and Kathy Olchin for providing illustrations. I wrote to Jerry, and he was kind enough to send me many of these pictures, and I had his name on the bottom for credit of the pictures. But I appreciate them actually sharing this with us. And again, that paper is available. If you go to his website, you can download it from his website. So, thank you. That's it.
Very good.
Yeah.
Tangential. Can you show the diffraction image of the crack?
Yeah, the area disc.
I'm sorry?
The area, yes.
I know that's when you use a star test that you're looking for to see that.
Yes.
What there determines your, I mean, like, so you want to be concentric, of course.
Yeah.
What else are you looking for as a perfect image?
Well, you probably won't see the area disc if you have aberrations in your system.
Okay.
In other words, if the mirrors are slightly, or the optical system is slightly misaligned, it's going to degrade that.
It's going to become off center.
It'll become off center, and the lines will become off center. So you can use that to test your alignment and test the quality of your optics, and that's really the one of the big things.
So it's supposedly also if it turned out as
yeah.
What those look like in the area disc, right?
Well, it depends on the specific aberrations. If you have, for example, astigmatism, you have cylinder, it's going to be spread out. So it won't be round, it'll be spread. If you have coma, it's going to be off to one side. So there's specific aberrations, and there's, the high order low order aberrations are defocus and astigmatism or cylinder. The high order aberrations are things like coma, there's what's called trefoil, where there's things, but these are rarely a problem. The main ones are the low order ones like coma and cylinder. And you can tell that by looking at the pattern of the diffraction rings around in the area disc. Yeah. Yeah.
I lost track. What is its function, and are there any implications to
removing it? The posterior capsule. I think we were talking about the posterior capsule. The anterior and posterior capsule. The capsule encloses the lens to begin with. Okay. When you remove that anterior lenses, there's not much of a consequence to it. The posterior, I mean, the anterior capsule, you have to do that to get the cataract out. With the posterior capsule forms a barrier between the anterior segment and the vitreous. So potentially, if you have that opening, the vitreous material can move forward, or stuff in the anterior segment can move backwards. Now, that's usually not a problem. But when an ophthalmologist does this, they don't want to make that capsulotomy too big. If you make it more than 5 millimeters or so, you can create those issues. You want to keep it as small as possible, but you don't want to have it so small that it creates another problem when you're with your pupil. One of the solutions that was proposed to them, for example, was well, we can make a small capsulotomy, and when you go out, when you want to see clearly, we'll give you some eye drops that'll constrict your pupil. Now think about that. We're out, they want to drive 40 miles to get out of the city to look at dark objects. You don't want to constrict your pupil. You want to dilate a pupil so you can see things. So you want to have it at least as big as your fully dilated pupil. I think they compromised at 5 millimeters was as high as it was safe to go on that. So, and I'm not familiar with all the complications you can get from that, but it's something to be, that you have to pay attention to when you make that opening in the back of the eye. Yeah.
So what happens to the material that was removed? Does it become part of the vitreous humor and then just kind of dissolve?
Yeah. Well, a lot of times it'll just spring back, because if it's under tension, it'll spring back. Otherwise, it just flops down and stays out of the way. So as long as it's outside of your optical path, it's not an issue. So if it gets into, if it for some reason floats around your vitreous, it can be a problem. Yeah. So, but I don't think that's usually an issue. The secondary cataract is actually fairly common. So these procedures with the laser posterior capsulectomy or capsulotomy are fairly common. So people do that.
So it doesn't just like detach and just start floating around.
I don't think it floats around. I think there's a little bit of an attachment on one end of it, so it just kind of stays, and it shrinks up with time as well, so it stays out of the way. Yeah.
Would an astronomer want the replacement lens set up for focus at vision in the distance or close up?
Distance or close up? You would probably, well, with us as an astronomer, it's I don't think it's going to make much of a difference, because you can adjust your focus on your telescope to accommodate. So, for example, when I've got a fairly strong myopic correction. So if I take my glasses off, this is what's in focus here. Everything else is blurred off in the distance. I'm legally blind without glasses. Sometimes I'll take my glasses off so I can get closer to the lens, and I just have to adjust the focus to get it clear. So I can adjust that with the focus tube on the telescope, or I can leave my glasses on and it has a different focus position. The advantage of having your cataract or your intraocular lens for distance, when you look through a telescope and adjusting, if you want to show somebody else, it will probably be in focus for the other person. Because when we wear glasses, we're usually using glasses for distance, and that allows you to, so your focus is for distance, and you'll be similar to other people who are looking through it. So I usually wear my glasses now when I'm looking through the telescope, so if it's in focus, and I want to show somebody else, I'll bring them up, and they won't have much to change their focus. If I have my glasses off, it's actually a pretty big difference. So.
In the 2026 spring edition of the NCRL newsletter, Carl Wenning had the editor, had this procedure done, and he had a 2-page account of what he went through.
What he went through.
So it's interesting to look that up. Just go to the NCRL page and go to newsletter, the latest one.
Yeah.
He chose to preserve his near vision.
Near vision, okay. Yeah.
Mm-hmm.
So he was So he was probably focusing for 25 millimeters, something, or 25 centimeters, something like that, for reading distance.
Yeah, he wanted things close to him, the desk and things, to be his priority.
Yeah, I think it's personal preference, whether you're used to wearing glasses or if you prefer not wearing glasses for what you do most of the time.
I can see how it would be nice if you enjoy naked eye astronomy, like
Yeah,
having distance vision
Yeah.
would be maybe better.
yeah, yeah. Although even if you had near vision, it's nothing lasts for 1.6.
Yeah.
See, you can have a pair of glasses for distance, or you would probably want to have a pair of glasses for distance anyway. The other
Jay?
thing is interesting about a cataract. Cataracts, if you could look at a cataract, it would look yellow. That's because it absorbs blue light. When you take the cataract out, people report seeing blue much more vividly, and things look much brighter because it filters. The cataract filters your eye. In fact, some people, I think they've said they can see down into ultraviolet a little bit further, at least deeper purple.
There was a story about that in the Sky Telescope. I think it was January.
Yeah,
So the guy. So normally the plexiglass is coated to stop ultra to stop UV light.
sub UV. Yeah,
And he mixes them.
yeah.
That he wanted to uncoat lenses and he promised to wear sunglasses. Always when he's outside.
Yeah.
Because it can damage your retina.
Yeah, yeah,
Because
yeah.
normally the natural lens, I guess, stops UV light.
Yes. Well, there's two things that stop UV. One is the cornea, but the cornea transmits down to about 380, I think it is, and I've actually measured the corneal transmittance. The lens cuts off at about 400.
Okay.
The crystalline lens. So when you take the lens out, you get just a little bit deeper into the UV.
So anyway, but he reported that he put it set on Venus and Jupiter.
Oh yeah.
That he actually put optical light filters on them.
Yeah.
And he was able to see infrared or ultraviolet.
Yeah.
And it was wrote about that.
Yeah.
In January.
Oh, that's interesting.
Everything looked yellow to me
Yeah.
until I had to until they put the new lenses in.
Oh.
I couldn't see blue in the sky.
Oh, we couldn't see blue in the sky. Yeah. Yeah.
They put the lenses in, and I didn't know you could get near or far. They just said far is good, and then you
wear glasses for up here. Yeah. Yeah.
But it worked out pretty good.
Yeah, I think most of the IOLs, intraocular lenses that are put in, are probably in for distance. But you can, if you have a discussion with your ophthalmologist, they can choose what you're most comfortable with, and it really depends on what you like to do, if you're working, what your career is, what kind of things you enjoy, and they can adjust for your needs. But you have to have that discussion with them about it, and don't just accept what they have.
I think you can get what's called toric lenses.
Yeah, yeah,
a progressive type.
Yes.
So you can get both, but then it's a little tricky.
Yeah, it's a little tricky. What they do is they'll put different parts of the lens, like the periphery, they would adjust for far. I don't know if it's periphery or central. And central would be for near. So when you look at something, you get an object that's going to have, it's going to be very clear, but then there's going to be some that's blurred, and your brain will select the clear version part of it. You have to adapt to it and so you'll be able to see things clear. You're always going to have this clear, and I don't know, people that have them seem to be happy with them. You get, and I think you can get contact lenses like that as well.
I had contact lenses like that. I didn't like it.
Yeah. Some people don't like it. For me, I think it would drive me crazy being able to, or seeing things and then having this blur circle around them all the time, from the other part of the lens. So, so there's a lot of people working on lenses now. The other thing that has been suggested, and I don't think this has really come to production yet, having an intraocular lens that would change its shape based on the ciliary muscle. So you would recover some of the natural accommodation from that, but I don't think that has really worked out yet. I know people have talked about that, and they're looking at materials that could behave that way, just like a normal lens, but I don't think it's actually come to anything that's clinically practical at this point. So, yeah.
Would it work to do a near lens in one eye,
and far another eye? Yeah. That's
sort of out.
Yeah, that's another approach, and that has been done with some people, and you can for some people you can do that with contact lenses as well, and I think you can do it with intraocular lenses.
I do that with my contact
I have
lenses.
that with my.
You have that with yours? Okay,
Yeah,
yeah.
monocular vision, they call it.
Yeah.
And your brain adapts. So I got it set for far and medium.
Yeah.
Still use readers for close.
Yeah. Are you comfortable with that when you're?
Yeah. They got to be in the right eye though. Because my brain, it really hurts my brain. I can still
Yeah.
see, but then something's wrong.
Did you put it in backwards? ever?
Yeah. Oh, yeah. All the time. Yeah. Not that.
So
Yeah, mine,
Zoom
mine
that.
was totally obvious.
Well, that's sort of like zoom lens. You can change the size of the image on that. You
Right,
mean?
well, I mean, I just didn't know if there was a way that a permanent lens for a cataract could
Could.
change.
Well, that's what I mean with the lens that's flexible, that you can get far and near. A zoom lens would change the magnification,
Right.
and I don't think that's anything that's people have been able to do yet.
He's pretty cyborg like that, though.
Yeah.
So they can tailor the lens, right? Because I had a friend that had them replaced. She used to have like 2280 vision, and then after it was 2020.
Yeah.
But
Yeah.
only in the one eye that was done. So,
Yeah.
so then when the second eye got done, then it was both eyes.
In both eyes, yeah, yeah. You can select the lens, the particular lens that you're most comfortable with or most comfortable dealing with.
Could you have the lens put in the other eye, even though it doesn't have a cataract?
No, that's
Just at least.
yeah.
Now you don't need glasses at all.
There's some controversy about that, whether you want to replace a clear lens, clear crystalline lens, a clear cataract is what people say. Some people said, yeah, let's go for it. People would be happier with an IOL to correct their vision. Others say, yeah, there's risk. There's always risk when you're doing an operation. If you've got a good eye, there's no sense in putting that through risk. So there's always some risk with getting better vision. I don't think that's done in practice.
I would still need to put contact in this eye. Well, this one's permanent.
Yeah.
Fixed.